Hello everyone, this is Shivanshu Gupta. Welcome to Engineering Hotspot. So, in this lecture series, we are covering the detailed solution of GATE 2023. So, whatever questions that has been asked in the mechanical engineering department, all the questions we are covering. And here we are covering the questions in the subject-wise manner. So, up to now, we have covered the three subjects question, that is the production engineering, including material science. Second one is the thermodynamics, and third one is the heat transfer. Today we are going to cover the whatever the question that has been asked from the fluid mechanics subject. So in this subject, basically we can see that total 5 question has been asked, and out of that 2 question were for the 2 marks, and remaining were for the sorry 2 question were for the 1 mark, and remaining 3 question were for the 2 marks. So total we can see that 8 marks question has been asked in this question paper. So now if we talk about the highest weightage subject from the gate point of view, so that is the production engineering. In the first lecture we have seen that total 10 questions has been asked including material science, and that has the total 17 marks out of the 100 marks. So that is why we can say that it has the very high weight percentage of the number of questions that has been asked there. So you can watch our complete lecture series on production engineering subject in our app and engineering hotspot YouTube channel by subscribing at just a price of 299 rupees. So go and purchase that one. So right now what we will do, we will start the one by one all the question that has been asked from the heat transfer fluid mechanics subject. So here you can see that in the first question, air with density 1.2 kilogram per meter cube, kinematic viscosity 1.5 into 10 to power minus 5 meter square per second, flows over a flat plate with a free stream velocity of 2 meter per second. The wall shear stress at a location 15 mm from the leading edge is given by tau W. What is the wall shear stress at a location 30 mm from the leading edge? So what is there? Air is there that is flowing over a flat plate at a velocity of 2 meter per second, right? And we have given the wall shear stress value, that is TW, tau W, at a location of 15 mm from the leading edge of the wall. Along with that, we have to find out the value of what is the wall shear stress at a location of 30 mm from the leading edge. So to find out this, first of all, we have to find out what type of flow is taking place over the flat plate, whether this is the turbulent flow or the laminar flow. To get that, we have to calculate the value of Reynolds number, that is given by V L divided by nu. Here nu is the kinematic viscosity. Now we will put all the values here. So we will get V, we have given 2 into what is the we have to actually find out the stress at a location of 30 mm. So we will take that. So this will be 0.03 meter divided by nu value is what? Nu value is 1.5 into 10 to power minus 5. Now, when we will solve this, we will get the RE value, which is equal to 4,000. And as this value is less than 5 into 10 to power 5. So that's why we can say that this is a kind of a laminar flow. And for the laminar flow, the wall shear stress is directly or inversely proportional to length x, under root of length x. So that is why we can find out the wall shear stress tau wall 2 divided by tau wall 1 is equal to under root of x1 divided by x2. right? They are the inversely proportional. Now we will put the value here. So x1 value is 15 divided by 30. This will give us the value of 1 by under root 2. So now we will have the wall shear stress at 30 mm. So tau wall will be is equal to at a location of second location, that is of 30 mm, tau wall 1 divided by under root 2. So here we can see that option number D is the option that is matching with our solution. So that's why this will be our right answer. So now what we will do, we will go for the next question. Now this is again for the 1 marks question. So here consider an isentropic flow of air with a specific ratio of 1.4 through a duct as shown in the figure. The variation in the flow across the cross section are negligible. The flow condition at location 1 are given as follows. P1 is equal to 100 kilopascal, rho 1 is equal to 1.2 kilogram per meter cube, U1 is equal to 400 meter per second. The duct cross-sectional area at location 2 is given by A2 is equal to 2A1, where A1 denotes the duct cross-sectional area at location 1. Which one of the given statement about the velocity U2 and pressure P2 at location 2 is true? So we have given some of the values at location 1, and now we have to find out the values, respective values for the location 2, right? And we have given 4 options out of that, so we can find out the value. So to find out what will be the value here, so we have to find out the value of Mach number. So how we can find out the value of Mach number? So Mach number ma is given by velocity of the fluid divided by the velocity of the sound, and the velocity of the sound is given by gamma r t. Here we don't have given the t value, so t value we can find out with the help of, how we can find out that, we can find out t1 will be is equal to t1 divided by rho r. So when you will put this, you will get the value of t1 as 290.6 Kelvin. So we can see that what is the Mach number. So Mach number here will be at the entry location. So Mach number will be V value we have given. How much we have V value we have given? So V value we have given of 400 meter per second divided by rho is 1.2. Sorry, gamma we have to put. So under root of 1.4 into 287 into T1 value is 290.6. So now when we will solve this, we will have the MA value that is coming out to be 1.017. That is greater than the value of 1. Okay, so what we can say, as this value is greater than the 1, then the flow is what type of flow is inside the this this is the supersonic flow. And for the supersonic flow, this kind of cross sectional area will act like a nozzle, and if this will act like a nozzle, that's why u2 will be greater than u1 and p2 will be less than p1. So that's why option number C will be the right option. So in this question we have given the inlet values, some of the pressure, density, and velocity, and we have to check what will be the velocity and pressure at the outlet section. So that we have find out with the help of the Mach number. That was also very easy question. Now let's move to the next question. That is our third question. So in the third question, we have given a velocity field for a two-dimensional flow that is given by Vxy is equal to Kxi minus Yj, where K is equal to 2 second inverse. The coordinate x and y are in meters. Assume gravitational effect to be negligible. If the density of the fluid is 1000 kilogram per meter cube, the pressure at a location at the origin is 100 kilopascal. The pressure at location 22 is in the kilopascal we have to find out. So we have given the pressure value at the origin. Along with that, we have given the density of the fluid. So now we have to find out what is the pressure value at location 2. So how we can find out that? That we can find out if we apply the Bernoulli equation in between the origin and a point which is at 2 meter. So this can be done by P1 divided by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. Now g will be cancelled from the denominator. So we can write P1 plus V1 square by 2, or we can multiply rho here. So rho V1 square by 2 is equal to P2 plus rho V2 square by 2. Now here V value is given by K into Xi minus Yj. So along with that, we have given the P1 value, that is the 100 kilopascal. So here we will put that in the kilopascal. So we will convert the kilopascal into the pascal. So this will become 100 into 1000 plus rho is what? 1000 into V1 value we have to find out. So V1 will be is equal to K is 2 into what is the Xi value, that is at the origin. This means this is 0 I minus 0 j. So this will give us the value of V1 is equal to 0. So now what we will do, we will put here V1 is equal to 0 is equal to P2, that is what we have to find out at pressure at the second location, plus 1000 into what is the V2 value. So V2 will be given by 2 into, here V2 value we have to find out at 2 location. So this will be 2I minus 2j. So this V2 will become 4I minus 2j. Sorry, 4I minus 4j. Right? So now, so we will find out the magnitude of V2, that is given by 4 square plus 4 square, that is equal to under root of 32. So now we will put here under root of 32 square. That will become what? That will become 32 divided by 2. So when you will solve all this, you will get the P2 value, and this P2 value is coming out to be 84,000 pascal. That is 84 kilo pascal, right? So with the help of Bernoulli equation, we managed to solve this question and we got the P2 value, and this P2 value is equal to 84 kilo pascal, right? So now what we will do, we will move to the fourth question. So here is our fourth question, that is given by, consider a unidirectional fluid flow with a velocity field is given by V x y z t is equal to u x t I, where u 0 t is equal to 1 if spatially homogeneous density field varies with the time t as rho t is equal to 1 plus 0.2 e to power minus t. The value of u at 2 and 1 is what? So we have to find out the velocity value at point 2 and 1. Assume all quantities to be dimensionless. So how we can find out this value, u value, when we have given the rho as a function of t? So we can find out with the help of the continuity equation, and continuity equation for the unsteady flow, that is given by rho du by dx plus rho dv by dy plus rho dw by dz plus d rho by dt is equal to 0, right? But here we have given u is a function of x and t only, so that's why these two terms will be removed. So the we are left with only rho du by dx plus d rho by dt is equal to 0. So now we will put all the values here. So rho value is given by 1 plus 0.2 e to power minus t du by dx plus t by dt. So here we are differentiating this rho value, and this is 1 plus 0.2 e to power minus t is equal to 0. Now when we will differentiate this and equate it to 0, so we will get du by dx. This du by dx will be given by e to 0.2 into e to power minus t divided by 1 plus 0.2 e to power minus t, right? This is how we will get the du by dx. Now to get the u value, we have to integrate this with respect to x. So when we will do that, we will have the u value. This is given by 0.2 e to power minus t divided by 1 plus 0.2 e to power minus t x plus c. C is what? A constant. Now what we will do? We will try to find out this constant value, as we have given one condition. What? U at 0 1 is equal 0 t is equal to 1. This is what we have given, right? So when we will put this, we can have the value t is equal to 1, right? So when we will put u is equal to 1 and x is equal to 0, so we will get one value of c1, that is coming out to be c1 is equal to 1. Now what we will do, we will put this value in the u, and we will have, so now we will try to find out the u value at 2 and 1 location, right? So how we can find out this? We have find out the c1 value. Now we will put everything here to get the final value. So 0.2 into e to power, so e to power minus t will be, this will become minus 1 divided by 1 plus 0.2 e to power minus 1. Along with that, this x will be multiplied by 2 plus 1. So this will give us the value of u is equal to what? U will be is equal to 1.137 meter. So now we will move to the next question, that is the question number 5. So the figure shows two fluids held by a hinge gate. So here we have given two fluids of different densities, right? One is of 1000 kilogram per meter cube, and the second one is of 2000 kilogram per meter cube density, right? Which is hinged by a, which is held by a gate, and that is hinged at here at the bottom. The atmospheric pressure we have given P1 PA is equal to 100 kilopascal, the moment per unit bit about the base of the hinges we have to find out. So what is the moment per unit bit we have to find out with respect to the base? Take the acceleration of the gravity is 9.8 meter per second square. So how we can find out this moment with respect to the bottom hinge? So to find out that, we can use this kind of pressure diagram. So with the help of this pressure diagram, we can easily find out this value. So how we can find out that? Let's see this. So to find out this, so what we will do actually, so here this DE line is showing what is the pressure that is being acting because of the first fluid of density 1000 kilogram per meter cube, and here this BC line is representing the total pressure that is acting at the bottom of the surface. So now what we will do, we will try to find out the first of all the pressure value, and then with the help of pressure value we will try to find out the force. Once we will have the force, what we will do next, we will try to find out the value of that force where this force is acting with respect to hinge, and then we will multiply that to get the value of our total momentum that is acting. So let's start that. So first of all we will find out what is the pressure that is acting at DE. So we can find out pressure P1 value that is given by rho 1 G H1. So we can find out 1000 into 9.81 into 1, that is given by 9810 Newton per meter square. Now next, once we have the P1 value, we can find out the net force. So net force will be is equal to F1 is equal to area of this ADE triangle multiplied by the width. So this area will be given by 1 by 2 into 9810. What is the 9810? 9810 is the DE value. Along with that, what is the AD value? So AD value is 1 multiplied by the width. Width is given by 1. So that's why we will get the final net pressure F1 is equal to 4905 Newton. Now similarly, we will try to find out the F2 and F3 value also. So to find out the F2 value, we again need what is the value of BF. So BF will be is equal to DE. So we can find out the F2 value that is given by. So what is the F2 value? So F2 value will be is equal to, so F2 value will be is equal to area of this DEBF. So what is the area of DEBF? That is given by, area of the DEBF will be given by 2 is the height multiplied by this BF. BF will be is equal to DE, that is 9810 multiplied by the width. So we will get the F2 value, and this F2 value is 19620 Newton. Now once we have the F2 value, we can find out the F3 value also. So the F3 value will be what? So to have the F3 value, we have to find out what is the FC value. So how we can find out the FC value? So we can find out the FC value that is given by pressure. So this is rho 2 G H2. So rho 2 will be what? 2000 into 9.81 into 2. So that is why this value comes out to be, this value is coming out to be what? 39240. Now we can, once we have the FC value, so we can find out the F3. So F3 will be given by 1 by 2 into FC is 39240 multiplied by width. Width and the height. Height is 2. So we will multiply here by 2. So we will get the F3 value is equal to F3 value is 39240. Once we have the F3 value, we can find out the where these F1, F2 and F3 are acting at from the top. So first of all, we will find from the top, then we will try to find from the bottom. So location of the forces from top will be is equal to F1 will be is equal to 2 by 3 multiplied by 1, that is given by 2 by 3 meter. F2 will be is equal to 1 plus, that is 1 is up AD plus half of this dB. So this will be 1 plus 2 by 2, that is equal to 2 meter. Then F3 will be is equal to, F3's location will be 1 plus 2 by 3 into 2. 1 is up to AD, then 2 by third of the EF. So this will come out to be 7 by 3. Now these are the distances from the top. Now we can find out the from the bottom also. So from the bottom, when the total from the top to bottom length is the 3 meter. So the distance of the location of the force F1 from the bottom. So now we are finding the location from the bottom. So when we will try to find out the location from the bottom, so we have to subtract this from the 3. So 3 minus 2 by 3, that is given by 7 by 3. For F2, this will be 3 minus 2, that is 1 meter. This is also in meter. And for F3, this is 3 minus 7 by 3, that is coming out to be 2 by 3 meter. So now we have the all the forces. Along with that, we have all the locations of those forces. So we can find out the moment about the hinge. So moment about the hinge will be is equal to F1 into 7 by 3 plus F2 into 1 plus F3 into 2 by 3. We have F1, F2, F3 value. When we will put, we will get the total net moment is equal to 57,225 Newton meter per meter. So now we can find out in the kilonewton, this will be 57.22 kilonewton meter per meter. This is the value, final value that we have to find out. So now we managed to solve all the 5 questions that has been asked from the fluid mechanics topic. So here what we have done actually in this question, we have tried to find out the what is the total force that is acting on the top, and then what is the total force acting on the bottom side, and then we have to we have multiplied those by that forces from the what is the location with respect to the hinge, and finally we got the momentum. So this is it for this lecture. Thank you for watching. Goodbye.